Hey everyone, welcome back to our channel. Today we are going to talk about one of the most important equations in quantum mechanics. That is the Schrodinger equation. We'll be exploring what it is, how it works, and what it tells us about the nature of reality at the quantum level. The Schrodinger equation is a cornerstone of quantum mechanics. It describes the time evolution of quantum states. Now, in this video, we'll provide a detailed derivation of the Schrodinger equation from first principles for a non-relativistic particle that lives inside one dimension. We will begin with the classical energy conservation equation and use the de Broglie's relation to express it in terms of the wave function. We will then rewrite this equation in terms of the Hamiltonian operator, which will then lead us to the Schrodinger equation. Now, along the way, we'll also explore the physical and the conceptual implications of this equation. That might include the probabilistic interpretation of the wave function and the role of uncertainty in quantum mechanics. Finally, we'll also discuss some of the key applications of the Schrodinger equation that includes, but is not limited to, the calculation of energy spectra and the behavior of systems in the presence of external fields. So I'll start by saying that the Schrodinger equation is one of the foundational equations of quantum mechanics, and it describes the time evolution of a quantum state, which can be thought of as a mathematical object that contains all the information that we have about a physical system. So a quantum state is what? It is a mathematical object that contains every single piece of information that you can have about the object, right, of that physical system. So in this video, again, we will derive the Schrodinger equation from the first principles and we'll explore its implications for the nature of reality at the quantum level. So let's start with the derivation, right? So I'm going to start by considering a non-relativistic particle. Let's suppose that this is my particle and it has a mass m and it lives inside a one dimension. So let's say it lives on this line, right? Let's say that this line is x-axis, right? So again, we have a non-relativistic particle that has a mass m and it lives on a one-dimensional axis. Now it moves under the influence of a potential energy function. So this particle is going to move on this line. However, there is some potential that acts on this particle, and we're going to say that that potential is some v of x. So the potential is v, and it is a function of x since it's moving in the x dimension. Now, the quantum state of this particle can be represented by what is called a wave function. So the quantum state is represented by a wave function, and we use psi. So sometimes I might write psi like this, or sometimes I might write it like this. Let's pick one notation, and we'll then stick to it, right? So let me say that, let's use this symbol, right? Okay, so this is the wave function, which is basically the quantum state, right? And as I have mentioned before, a quantum state is a mathematical object that contains every piece of information about a physical system. So for this particle, every single information that you can have for this particle is in this wave function psi. Now, that means that this wave function should obviously be a function of the position of the particle and the time, right? Now, this state, quantum state, should satisfy our Schrodinger equation. I'm going to write this Schrodinger equation over here, but of course, we are going to see where that equation comes from. So let me just write it down. The Schrodinger equation is iota h bar partial derivative with respect to time. So this, I have this notation that I use sometimes. So if it is partial derivative with respect to time, then I represent it as partial and a small subscript t at the bottom of it, right? So I'm just going to leave this over here so that you know that this is what I'm talking about, right? Okay, now this is the time derivative of the wave function psi. So let's stick with this thing. But remember, the wave function is a function of both x and t. And this thing is equal to the Hamiltonian operator that acts on the quantum state psi, right? So it is something like this. Again, this H with a little hat on top of it is the Hamiltonian operator. You can think of it as the total energy operator. So when this Hamiltonian acts on the quantum state, it should give you the information about the total energy of the system whose quantum state psi is, right? Now, the Hamiltonian operator further can mathematically be written as minus h bar squared over 2m partial x squared plus v of x. Again, this partial x squared is just partial over partial x, and then it is basically square of this, so it's the double derivative, right? So this thing, I represented it with partial x squared. So I hope with these two notations, you'll get the idea of, you got the idea of the notation that I use sometimes. You might not be familiar with it. You might also be using the same notation, but in any case, this should put it in your head that this is the notation that I'm using. So whenever you see this thing, you know that it is just this thing. Right. Now, we want to derive the Schrödinger equation. By the way, this Hamiltonian operator, which is written in this way, you will see why is it written in this way as well. But before I go any further, I want to tell you one more thing, that as I said, the Hamiltonian operator is the total energy operator. And you can see that this Hamiltonian operator, this thing is the potential function, which means it is giving you the potential energy of the system. So we have the potential energy over here. What does that mean? That means that this thing should be the kinetic energy of the system, right? Since the Hamiltonian operator is the total energy would be made up of the kinetic energy of the system plus the potential energy of the system. So the kinetic energy of the system, I'll write it over here as Ke, right? So the Hamiltonian is just the kinetic energy plus the potential energy. Right, so now that we have that out of the way, we're going to derive the Schrödinger equation, and we're going to start with the classical energy conservation. Now, we know that the classical energy conservation equation states that the total energy is half mv squared, which is just the kinetic energy, plus the potential energy of the system, right? Now, in this equation, v is the velocity of the particle that we're talking about, right? And m is the mass, as we know, and this v, capital V of x, is the potential function. Now, we can express this equation in terms of the wave function by using what is called the de Broglie's relation. So the de Broglie relation states that the total momentum of the system, of the particle, is just h bar, which is the Planck's constant, divided by the wavelength of that particle, right? So it is not the wavelength of the particle, but it is the wavelength of the associated wave of that particle. So the particle has a wave. There's a wave that is associated to that particle, and this lambda is the wavelength of that wave, right? I can further write this down as h bar and 1. So this is 1 over wavelength. But we know that we define this 1, the inverse of the wavelength is defined as the wave vector, right? And it is written as k. So I can write this thing as h bar times the wave vector, k. So therefore, the momentum is given by h bar k. This thing is the de Broglie's relation. Again, p is the momentum of the particle, and lambda, this one, is the wavelength of its associated wave, and k is the wave vector, right? Now, using this thing, I can write the classical energy conservation in another way. Before I do that, it is also important to note that the kinetic energy of any system, which I wrote as half mv squared, but where does that half mv squared comes from? It comes from the fact that the kinetic energy is really p squared over 2m, Now P, from your classical mechanics, you know it is simply mass times velocity. So I put mass and velocity and I square this and I divide it by 2m. What do I get? I get this 1 by 2. One of the m's cancel with this one, so 1m is left, and then v squared. So that's where you get your half mv squared from. Right, now what I'm going to do is I'm going to rewrite this equation. Let me just highlight it for the sake of it. This equation, I'll rewrite it using this relation that we derived. P is equal to h bar times the wave vector. So I can write it like this. E is equal to 1 over 2 m times h bar k over iota squared plus v of x. Oh well, this iota, it should not appear in this equation. I'll tell you where does that part comes from. So let's just correct this thing like this. All right. Okay. So this is now our rewritten classical energy conservation. Right. Now what I'm going to do is I'm going to write this simply as E is equal to P squared by 2m plus v of x. And I'm sure now you know that how did I write this equation. Well, now the thing about quantum mechanics is that whenever you want to go from anything that you do in classical mechanics and you want to shift towards quantum mechanics, you do it in the form of operators. Now, that means that every single observable that you have in classical mechanics, such as momentum, position, energy, or time, these are treated as operators. So what you do is you promote a classical observable to a quantum mechanical operator. So just that promotion of an observable to an operator takes you from classical mechanics to quantum mechanics. So that begs the question that what would be the operator of these quantities that we see over here? Well, in these quantities, momentum and energy are our observables, right? And for these observables, we need to find out what operators are they, right? So again, we need to find out the operators P and E. I'm just going to put a little hat on top of them since we're talking about operators, and operators are denoted with a little hat on top of it. Okay, so I'm going to derive these operators, right? So the derivation of these operators is what we will do next, and then we'll go back to our deriving the Schrodinger equation. Since this derivation is required to understand the Schrodinger equation. As you know that over here, we arrived at this step. The next step is just to promote them to operators so that we can shift to quantum mechanics. And after that step only, we can move towards the final form of the Schrodinger equation, right? Okay, so let's start with the definition of the momentum operator in quantum mechanics. So the definition of this momentum operator in quantum mechanics is that it is written as, or it is represented as minus iota h bar partial x, right? So this is again in one dimension, right? So in one dimension, it is written as negative iota h bar partial over partial x. Again, h bar is just the reduced Planck's constant, and this thing is your partial derivative with respect to x. That is the position, by the way. Okay, next, what I'm going to do is I'm going to derive this operator. And the way that we do this is we take this guessed definition and we apply it to our quantum state, the wave function psi, right? So let's do that. I take this momentum operator and I apply it on the quantum state psi, which is a function of x. That would mean that I should get the momentum operator, which is minus iota h bar partial x. This is our proposed guess, and the wave function psi of x. Right. Now, what I'm going to do is I'll use the definition of this partial derivative and rewrite this whole thing on the right-hand side. So that would mean that this is minus iota h bar the definition of partial derivative with respect to x is in terms of limits, right? So this is just limit delta x goes to 0. And what we have is the partial derivative of the wave function psi of x. So we'll write it as psi of x plus some delta x, which is a little bit change in the position x, a little bit of deviation from its original path, minus the wave function as a function of its original path, right? So that is just x. And we'll divide all of this with this deviation in x that we do, delta x. This whole thing, this one, is the definition of this partial derivative with respect to x of this psi of x, right? Okay, all right. Here we have again used the definition of the partial derivative to represent the limit as delta x approaches to 0, right? So again, that is the definition of the partial derivative. Now I'm going to use the Taylor series expansion and rewrite this part of this thing, psi of x plus delta x, this one, right? Okay, so using the Taylor series expansion, I can express this psi of x plus delta x as, so let me just clean this up. So this is under the Taylor series expansion. I can rewrite it as, so I'm just going to put an equal to sign that this thing is equal to, under Taylor series, psi of x plus delta x partial over partial x of psi of x plus delta x squared over 2 factorial times partial x, the double derivative of psi of x. And then you can write this so on, right? So this is a Taylor series expansion, so the series continues. Now let's take this thing and substitute in this equation, right? In this thing. So what we get is p on psi of x is equal to minus iota h bar limit of delta x goes to 0. Now for this thing, we are going to use this Taylor series expansion. So this becomes psi of x plus delta x partial derivative with respect to x of psi of x plus delta x squared over 2 factorial partial derivative with respect to x, double partial derivative with respect to x of psi of x plus the other terms in this series, and then we have this delta x in the divisor. So in the denominator, right? So I'm going to write this like this, and delta x. Now we know that what is this? This is just minus iota h bar. And what is this entire thing? This entire thing is nothing but the partial derivative with respect to x of psi of x. You might wonder, what about these terms where we have delta x squared, and then we would have other terms in the series where delta x would be cubed, and then power 4, power 5, and so on. I have simply dropped those terms that are of higher order in delta x, since they would just vanish when delta x approaches to 0. So as delta x becomes smaller and smaller, and if I cube or square or take the power 4 of a smaller value, it becomes even more smaller. So it would just basically vanish as delta x goes to 0. So therefore, we have derived the momentum operator p hat is equal to minus iota h bar partial derivative with respect to x. All right. Now let's move our attention to the energy operator E hat. So I'm going to derive E hat now. I'm going to use the similar method, and I'm going to use the definition of the energy operator in quantum mechanics. Let's say that it is iota h bar partial derivative with respect to time, right? By the way, there's one thing that you might notice if you are already familiar with quantum mechanics, that momentum and position are the two conjugate variables. In the same way, time and energy are also two conjugate variables. So that is just something that I wanted to point out. As you can see in this thing, that for the momentum operator, the partial derivative is with respect to its conjugate variable, that is x, position. And for the energy operator, it is equal to iota h bar, partial derivative with respect to time, where time and energy are the conjugate variables, right? So that's something worth noting over here. All right, now let's take this energy operator, E hat, and let's apply it to our wave function psi of x. This time, by the way, we'll take E hat and we'll apply it on psi of x comma t, since the operator E hat is going to affect the temporal part of this quantum state, right? Since the partial derivative, it's with respect to time. All right, so once you do that, once you apply this thing on this psi of xt, you get iota h bar partial derivative with respect to time of psi of xt. Now I'm going to again use the definition of the derivative, and now I'll do this a little bit quickly. So this would be iota h bar limit of delta t, this time which goes to 0, of psi of x comma t. Now this time the change would happen in t, so t plus delta t minus psi of xt divided by the delta t, right? So again, let's use the Taylor series expansion and expand this thing. So under Taylor series expansion, this thing, let's highlight it again. So this thing under Taylor series expansion is your psi of x comma t is equal to psi of x comma t plus delta t is equal to psi of x comma t plus delta t partial derivative with respect to time of psi of x t, and then we would have plus delta t whole squared divided by 2 factorial of the partial derivative with respect to time, double partial derivative, and psi of x comma t, plus we would have the other terms as well. Right, now I substitute again this thing, this Taylor expansion, into this one. Right, so in this equation, let's put it and let's see what do we get. We'll get E hat on psi of x comma t is equal to, okay, so this would be something lengthy, iota h bar, and then, okay, so I'm just going to do this one trick. Let's just take this thing, copy, paste. Right, so we would have this thing, and by the way, I should leave some space over here since this thing is after that limit, right? So you're applying the limit, delta t goes to 0 on this thing minus this psi of x comma t divided by delta t. Right, again, I'm going to drop the higher order terms of delta t since they would vanish in this limit where delta t is becoming smaller. So if delta t is becoming smaller and smaller, then if I square that or cube that, that would be even more smaller. So I can just neglect it, right? So that would mean that this thing would just then become iota h bar partial derivative with respect to time of psi of t, right? So therefore, we have also derived the energy operator E hat as iota h bar partial derivative with respect to time of psi of t. So in summary, what we have done is we have used the definition of the momentum and energy operator and applied them to the wave function, the quantum state of the particle, using the partial derivative. And then we used the Taylor series expansion to simplify our expression, and we obtained the final form of these operators. So we have E hat, and now we also have this one, the P hat, right? So we have these operators now, and the next step is to put them into this equation over here, the classical equation, the classical energy conservation equation. So let's shift our attention back to that. So I'm just going to bring this, where is it? This one. Let's bring it down over here, and let's put it somewhere over here. And I'll write down our operators again as well. P hat is equal to minus iota h bar partial derivative with respect to x, and E hat is iota h bar partial derivative with respect to time. I should not put the psi over here since I've just written this operator E hat, right? So let's just clean this up. All right. So now the next step is to put these into this equation. So that's what I'm going to do next. So again, p hat is this thing. What would be p hat squared? It would be minus iota h bar whole squared partial x squared, right? So what would that be? That would just be iota squared is minus 1, and this minus squared would be just plus, so we get 1 minus because of iota squared, and h bar squared and partial x squared. So this is your momentum operator. Let's put it over here. So this becomes momentum squared becomes minus h cut squared partial x squared. Let's write it like this. So this, and then 2m is at the bottom, and then partial x squared plus v of x. And what about this energy? By the way, I had promoted these to the operators. That's why I'm writing it like this, just to go to quantum mechanics, right? Now, energy operator is iota h bar partial t. So I'll write it over here, iota h bar and partial derivative with respect to time. There's one thing that I'm missing over here, and that is the quantum state that all of this is acting on. So I'm just going to put that over here. And this is acting on this quantum state, which is psi of x comma t. And all of this thing is also acting on a quantum state. So let's clean this up. This thing. And it's acting on the quantum state psi of x comma t. This equation that I just wrote over here, well, really derived over here, is the Schrodinger equation for a non-relativistic particle in one dimension. So I'll write that down over here. So this is the Schrodinger equation for a non-relativistic particle that lives inside one dimension. Non-relativistic, by the way, just means that it is not moving closer to the speed of light. It's moving with the velocity that is very much smaller than the speed of light. Now let's look at this equation and let's try to analyze this equation. So I'm just going to keep this thing over here, and you can keep looking at this equation, and we see that this Schrodinger equation describes how the wave function evolves over time, right? And how is this wave function affected by the potential energy of the system? So this Schrodinger equation, it has profound implications for our understanding of the reality at the quantum level. Again, it tells us that particles at their most fundamental level are not point-like objects moving through space, but rather they're wave-like entities that spread out over the space and time, right? So that's what this wave function is telling you, right? The wave function spreads out over space and time, and so it's a wave function. It's not really a point-like object. The wave function of a particle contains all the information, by the way, as we have talked about it. So it is also inherently probabilistic in nature, right? So the wave function is probabilistic. The square of the absolute value of the wave function gives us the probability density. So what I'm saying is that if I want to find out the probability of a particle at some point or some position x or at some time t, what I can do is I can take this wave function psi of x comma t, and I can take the mod square of this thing. Once I do that, I get the probability density of finding the particle at that particular position x in space and at time t, right? Now, another important concept in quantum mechanics is what we call the principle of superposition, right? So this was probability. Now, the principle of superposition. The principle of superposition states that if I have two quantum states that are allowed for a system, so perhaps a particle of mass m can be in a state psi, right? Let's just say psi 1, and it can also be in another state psi 2. If this particle can exist in any of these two states, then any linear combination of them is also a state that the particle can exist in. That means that another state would be the linear combination of these two states. So these are the states of the particle that it can exist in. So initially we just saw the particle existing in psi 1. And then after some time you observe the particle in psi 2. That tells you that the particle can also exist in psi 1 plus psi 2 state. So mathematically, again, this means that if I have this function psi 1 and psi 2, and if these are the solutions to this Schrodinger equation, then any linear combination of them, psi 1 plus psi 2, which I should write as some alpha psi 1 plus some beta psi 2. Since these alpha and beta are the coefficients of this wave function, and this thing is also a solution to the Schrodinger equation over here. Right. So what does this do? This basically leads to a phenomena that is known as interference and entanglement of the states, right? So there can be some interference between the states and the particle can be entangled as well, right? So it's where the wave functions of the two particles become correlated in such a way that they cannot be described independently of one another, right? So that can also happen. Our wave functions can become so correlated that they cannot be anymore described independently, right? Anyhow, all in all, the Schrodinger equation is a powerful tool for understanding the behavior of particles at the quantum level. Its derivation from first principles, as you saw, is based on the de Broglie's relation and the energy conservation equation. And it describes how the wave function of the particle evolves over time in response to the potential energy of the system. The concept of the wave function and the principle of superposition have profound implications for our understanding of reality at the quantum level. And they're also essential for understanding the phenomenon such as interference and entanglement, right? So that's more or less the entire video. I'm just going to give some concluding remarks and end it with the fact that this, by just saying that the Schrodinger equation has revolutionized our understanding of the behavior of particles at the quantum level. Its mathematical formulation that is based on the de Broglie's relation and energy conservation equation has provided us with a powerful tool to describe the evolution of the wave function of a particle over time. Again, the wave function psi of x comma t is itself a probabilistic entity that contains all the information that we have about the particle. And it is governed by the principle of superposition that we talked about. And that principle of superposition allows for interference and entanglement between multiple particles. These concepts that we have talked about, by the way, they have profound implications for our understanding of reality at the quantum level. And they have led to the development of numerous technologies that rely on quantum mechanics. Despite its success, though, the Schrodinger equation is not the final word in quantum mechanics. And ongoing research seeks to refine our understanding of the quantum behavior and its implication for the nature of reality.